All right, so this lesson we're going to start looking at Newton's laws, and Newton's laws are three laws which Isaac Newton is generally given credit for. And the first of those three laws, which I call the law of constant motion, says that if acceleration of a object or system is zero, then the net force acting on that object or system must also be zero. What that means is if you add up all the forces acting on an object and you end up with zero as your answer, then the acceleration of that object is zero, or the state of motion. Its direction of travel and its speed are the same. So there's really two different situations where this would occur. We generally look at this in lots of detail in systems that are at rest, but remember, if you ever see the term constant velocity, that would also imply that the net force acting on an object is zero. The one thing I will caution you here is that constant velocity and constant speed do not necessarily mean the same thing, because you can have a net force acting on a system that's moving at a constant speed if that object is changing directions or that system is changing directions. The first thing to point out about this too is note that there can be forces that act on the object as long as they add up to zero. So Newton's first law does not say that in order for acceleration to be zero there can be no force acting on the object. It just says that the net force, the sum of all those forces, is zero. So let's look at some common forces that we come across in a daily basis and what some of the symbols you'll see me use through the course of AP Physics. The main reason why I pick these symbols is that they match the symbols you generally find on your equation sheet or the symbols that the College Board will generally use when they're talking about forces. So the first one of these is a force that we deal with all the time here on Earth, and that's an object's weight. Weight is technically the force due to gravity acting on a massive body. So when we talk about mass and weight being different things, they really are different things. Weight is how much force is gravity acting on this mass. Mass is just how much stuff is in this object. One is a vector, weight is a vector, mass is a scalar, how much stuff. So there are two ways you can calculate force due to gravity. The first one I have on the left, F sub g is equal to mg, where g is 9.8 meters per second squared. That will work anytime you're relatively close to the Earth's surface. The second one is a more general equation, what we would actually call Newton's law of gravity. Fg equals g, mass of one of the objects times mass of the other object divided by the distance between the centers of those two objects squared. Generally speaking, when you look at Newton's law of gravity, we could look at something like the orbit of a satellite around the Earth. We'd use big M to talk about the mass of the Earth, little m to talk about the mass of the satellite, and r to be the distance from the center of the Earth to the center of the satellite, center of mass to center of mass. So that's one common force that we deal with pretty much in any situation. If we're here on Earth, you should have weight as a force acting on the object. Another fairly common force is what we call a normal force. And a normal force I generally define as any contact force between two objects. It could be a block sitting on a table. The table applies a normal force on the block. The normal force always acts perpendicular to the interface between the two objects. Basically, whatever surface has the contact, the normal force is always perpendicular to that surface. Where you see it most frequently is something like a block sitting on a table or a block sitting on a ramp or something like that. We would talk about a normal force in that case. Now, in some situations, normal force and weight are the same. In other situations, normal force and weight may not be the same. So don't memorize in your head that normal force and weight are always the same, because they're not always the same. Even on a flat surface, they're not always the same, because if that surface is accelerating, things might be kind of funny. The third of what I call the common forces is friction. And friction comes in really two varieties. One is static friction, which we use Fs for. Basically, static friction is acting on two objects if the surfaces of those objects are not sliding with respect to one another. So if you look at where one object contacts another object, that point of contact is stationary. One thing to point out about static frictional force is that it kind of depends upon what the other forces are that act on the object. That we have an equation to measure the maximum static frictional force, and that's related to what we call the coefficient of static friction, the Greek symbol μs, and the normal force, Fn. So when we look at a situation like this, basically what this equation tells us is what is the largest value that static frictional force can be, and any value underneath that could be valid. It's a little different than kinetic friction, and kinetic friction is the friction that acts between objects when they are sliding across one another, when the surface is not stationary with respect to another surface. And generally speaking, with most types of surfaces, kinetic friction is a constant value related to the coefficient of kinetic friction and the normal force. And so there is a way that you can calculate kinetic friction right away. Now, in a lot of situations, if we're talking about an equilibrium problem where an object is at rest, in most cases it'd be static friction that we're working with. If we're talking about an equilibrium problem where an object is moving at a constant velocity, and a lot of times that would be kinetic friction. And the last of the common forces we come across quite frequently is tension, and I use Ft as a way to signify tension. And that's any pull from a rope, cable, chain, string, whatever you want to put in there. It's some sort of pulling force using a rope, a cable, a string, a wire, whatever it happens to be. Tensions are always pulling forces because, well, ropes, chains, cables, strings, wires can only pull objects. You can never push an object with a rope. So it always pulls in the direction of the rope, cable, chain, string, wire, whatever. So let's look at a couple of example problems. And the first example problem I have is 3 blocks, and I've labeled them A, B, and C. And they sit Block A sits on a rough surface where block B is sitting on a nearly frictionless ramp, and of course block C is just hanging out there in space. And what we want to do is find the tension in the cable, or both ends of the cable between A and B and the cable between B and C, in terms of the masses of the 3 blocks, the acceleration of gravity, and the angle of the ramp. Now this would be a pretty common problem that you might see in an AP Physics assignment. The main reason for this type of problem is it gets you to start to solve problems symbolically and think through how do I symbolically solve this problem rather than where do I plug the numbers in and calculate it. So let's do a couple of quick things. The first thing that we would want to do is draw a free body diagram. What are the forces acting on the objects and which directions do they go? So each one of them has gravity acting on them, and in each one of them it's acting straight down toward the center of the Earth. 2 of them have normal forces acting on them, block A and B, because they're both sitting on a surface. Block C has no normal force because it's not sitting on a surface. Now, there is a tension acting between block B and block C in that cable, and what I will propose to you is that the tension acting on block B's end of the cable and the tension acting on block C's end of the cable are actually the same numerical value. Now, if you take a step back and think about this for a second, you would have to realize that, yes, this has to be true. And the reason why this has to be true is actually the third of Newton's laws, what we call Newton's third law. And what Newton's third law really says is if one object puts a force on a second object, the second object applies the same force on the first object, So in this case, block C pulls down on the cable pulls up on block C. Block B is the cable's gonna pull up on block B, and that pull's gonna be dependent on how big block C is. That's tension. And well, block B has to be pulling down at the same tension. And so there's some weird interaction in here where these 2 tensions have to be the same. You can almost think about this as removing the string itself and having the force of interaction between block C and B directly. Same thing would be true with the force between block A and block B, that those values of tension have to be the same. Now, the one thing to point out is the directions may actually be different. And the last force that we have is the friction acting on block A. Now, you might say that there's some obvious problems here. There's some forces that don't all point the same direction. How does this work? I'll tell you, if you actually do the math, and I would actually encourage you to try this on your own. Try to do sum of forces on the entire system when we get done, and what I will guarantee you is that you'll end up with 0. So sum of forces equals 0 for all 3 blocks. It said they were stationary. So what this means for, block A, that tension and frictional force of A, these 2 forces have to add up to be 0. It's also worth pointing out that those 2 forces must also add up to be 0. So I can say tension 2 and the frictional force on A have to be the same. We could say tension 2, tension 1, and, well, looks like the x component of weight for block B, and the reason for that is we probably want to pick this to be the x direction and this to be the y direction in this problem. 3 of these forces act on this axis and only one acts straight down. Now you could do this other ways. You could say the x component of tension 1, the x component of tension 2, and the x component of the normal force, or the y components of all those equals the weight of the object. You could do it that way. I think it just makes your life a little bit harder because you don't have all of that information. And the last one that we have is that tension 1 and the weight of block C have to be the same. And that's because block C isn't moving in this case. So we've actually solved for one of the tensions. It's just MC times G. Well, that's nice because maybe I can solve for the second of those tensions. If I rearrange this so that tension 2 is in there and plug in what we know about that tension, we get MBG sine of theta. Well, remember, if we're breaking this into x and y coordinates, you can actually break that one up. And so we get tension 2 right there as mcg minus mbg sine of theta. If we wanted to, we can go one step further and figure out what is the smallest value of coefficient of static friction that could be acting between A and its surface. It's also worth pointing out that if there's no friction between this surface and A, that it's possible that maybe this system has to move. We don't know for sure. We'd have to do a little bit more work. So let's use a second example problem. And this is a classic example problem. You see I've modified it slightly by putting 3 blocks, but this is a good problem to kind of work out. This one's what I call the cable problem, or the box held by 2 cables problem. And here I've given you a box with a weight of 500 newtons, and I want to find the tension in each cable. So if we identify the forces, we have the weight of the box, which we know is 500 newtons. I'm going to call the one on the left tension 1 and the one on the right tension 2. So if I look at these 3, what I can say for sure is that sum of forces in the x direction has to equal 0, sum of forces in the y direction equals 0. In this case, well, we maybe could make one of these x and y. I guess maybe that works out since this has to be a 90-degree angle. That might just be an artifact of the angles I've picked. If we wanted to maybe do it generally, I'm going to call this direction the x direction and that direction the y direction. So I can say about the x direction is the x component of T2 minus the x component of T1 has to equal 0, and the y components of tension 1 and tension 2 minus the weight has to equal 0. So in this case, if I break up x and y components of tension 1 and tension 2, we get here my x components, here are my y components. And those are basically based on the fact that I've given you angles with respect to the horizontal. Now at this point, you should probably see I have 2 unknowns, ft1 and ft2. Those are the 2 unknowns I want to find, and I have 2 algebraic equations. This is a system of equations, 2 equations, 2 unknowns. It's possible to solve this system. So let's solve one of the equations, and I'm going to solve this one here, the first one, just because it looks a little easier to work with. And so I'm going to set them equal to one another, and I'm actually going to solve it for ft2, and then I'm going to do substitution. You could solve it for ft1 and do substitution and get the same result. So let's do my substitution for ft2. And then what I now have is an equation with only one unknown, ft1. So I'm going to solve it, add 500 to both sides, factor out the t1, and then I get some funky thing with a bunch of trig functions in it. This is ultimately going to be some number that I can calculate out, which if I get my calculator out, it's 1.155, and then I can divide it out and find that ft1 is 433 newtons. What I could then do is substitute it in right there for ft2, and I get ft2 is 250 newtons. I can guarantee you, just because of what I know about this system, that those 2 values seem pretty correct or pretty logical. So those are some quick equilibrium problems and some things to deal with forces in equilibrium. Equilibrium is one of those things that's a really important topic when we start to think about forces in physics.